printf here at the end, which is what happens when we exit the loop. Okay, so obviously that's not a pretty picture in any way to have to draw, and this is a fairly simple program. And this drawing these things does get pretty complicated, but hang in there with me on this for a moment, and we'll get away from the graph eventually, and I'll tell you a more realistic way of doing this. Anyway, once you have the graph, you can calculate the cyclomatic complexity by looking at the number of enclosed regions. Now, enclosed region is this region here, right, because it's enclosed by the loop, and then this region here is enclosed. So number of enclosed regions plus 1, or 3, which is cyclomatic complexity. Now also, you can calculate it by taking the number of edges, which are the arrows, these guys here, and then subtracting the number of nodes, these are the bubbles here, and then adding 2. And you should get the same answer. Now, that's the hard way to calculate this. Draw the graph and then look at the regions and edges and go from there. Now, what about a somewhat easier way to do this? Now, the easier way to do this is to count the number of branching and or looping constructs and add 1. So we got an if here. That's a branching construct. You don't count the else because the else is part of the if. You got a 4. Okay, so now we're up to 2. There aren't any others, so 2 plus 1 is 3. This technique seems to work. This counting the branching and looping constructs and adding 1 seems to always work. So I would suggest that quick and dirty estimate of cyclomatic complexity, you go that way and skip drawing the graph, because obviously drawing the graph is going to get really painful as the program gets more complicated. The only complication to remember with count the branching and looping statements and add 1 is that in the case of a switch case construct, each case block counts as a 1, but the default does not. So just remember that, and then think about that for a moment, and you'll see why. Okay, let me get back to normal drawing here. Okay, now, yeah, moving on to basis paths. Let's look at the basis paths and basis tests concept that McCabe defined, because this actually does have some utility to you. So to define the basis paths, basically what you do is you pick a path through the flow chart. So we could say we've got 1, 2, and 4 is a path, okay? And then I'm going to pick a path that's going to add 1 more node, 1, 2, 3, and 4. And then I'm going to pick a path that's going to add another uncovered node if there is one, or if not, then another uncovered edge. So I'm going to go 1, 2, 3, 3, 4. Basically, you're adding the minimum possible number of new edges or nodes in each of the subsequent paths, and those are what McCabe referred to as the basis paths. Now, then what you would do, having defined the basis paths, you would then select the data more or less arbitrarily that would cause the control flow to move along those paths. So a set of basis tests would be n equal 1, and n equal minus 1, n equals 0, and n equal 1. Now, what possible good is this to you? Well, basically, the number of tests required to get basis path coverage is about the same most of the time. I can't think of any exceptions, but it can be used as a general approximation of the number of different tests that you would need to achieve decision coverage. So if you're talking to a programmer, or you're looking at a programmer's unit tests, or if you're a programmer and you're doing unit testing and you want to just quickly check, have I gotten decision coverage without necessarily using some sort of tool to figure that out, just look at the number of tests that you've got, as in this case, and look and quickly calculate the cyclomatic complexity using the rule of thumb that I gave you earlier, and then you're good to go. You know, if you're it's equal to or greater than cyclomatic complexity, then you probably have achieved decision coverage. If not, then you probably haven't. So that's one practical application of this as well. Now there's another way to calculate the cyclomatic complexity above and beyond just that counting it up thing. And the counting will work fine if you're looking at a single function or something, but obviously if you're dealing with a file that's full of a bunch of class definitions or functions or something like that, it's going to be kind of tedious to count them. There are some tools that will help you with this. So for example, there's out on sourceforge.net, there is a free tool that will do cyclomatic complexity calculations for the Java. And I wouldn't be surprised if there's a C++ one floating around out somewhere too. So that's an option. Now there's also McCabe's battle map tool, which I believe is still sold. That is a somewhat bigger ticket item than a free download off of SourceForge, to say the least. Okay, so far we've been looking at control flows, so let's move on to look at data flows briefly. So what we can do to look at data flows is to use something that's called set use pair coverage. So basically what you're doing is you're looking at when a variable is assigned a value and when that value is subsequently used prior to that variable being assigned again. In other words, the value being overwritten. So what you're doing is you're watching a value flow through a sequence of variables with set use pair testing. So to go back to this Fibonacci program here, to analyze the set use pairs, what you would do is you would identify the different variables. In this case, so you've got the variables here. Let's see those guys there, I, N, P, 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 and C. And then what you have to do is you have to look at the lines where the variable is set and then where it's subsequently used. And so, for example, let's take a look at N here. We got N, we've got a set of N on 5, and then a use of N on 6. And N is only set at line 5 or line 8, right? So we set it here, and then we use it in 6. We could set it here, and if it's greater than or equal to 0, then it would be used here in the comparison. And then it would also subsequently be used here. Now, if it's less than 0, it's set and then used here, and then it's set again here and then used down here. So that's the 8 and 21. So we can then look at the values required to force the code to flow through those particular sequences that we've identified. And if we look at the values that we came up with for basis test coverage, then we can say, okay, well, what if we test with n equals 0, n equal 1, and n equal minus 1? And what you see is that you're not necessarily going to get all of the data flow coverage that you might want to get out of this set of values, because take a look at the situation where C is going to flow into P here, right? The value in C flows into P, and then value P flows into PP, and then it flows back into C here. So there are interesting data flows that can occur that are not necessarily going to be addressed by control flow coverage. So that's not necessarily a heartening thing to know, because I have not seen, and I'd be interested during the Q&A session if anybody has, I can certainly mention it. I have not seen any tool support for data flow coverage, at least not commonly out there. So without a tool to do that, obviously that would be tedious in the extreme. Now, Brian Merrick, in his book, The Craft of Software Testing, took a very different perspective on white box testing, and it's